Hello everyone and welcome to my talk on search problems in trees with symmetries, or more specifically near-optimal traversal strategies for individualization refinement algorithms, which is joint work with Pascal Schweitzer. The agenda for today will be that I will be first talking about the motivation for what we are looking at, then I will give you a model, an abstract model, and then we will talk about some upper and lower bounds in that model. Okay, so let's start off with the motivation for what we are doing. And so the main motivation is the so-called graph isomorphism problem. And the graph isomorphism problem gets as input two graphs, G1 and G2, and asks the question whether these two graphs are isomorphic or structurally equivalent, or a more formal way to put it is to ask whether there is a neighborhood preserving mapping from the vertices of G1 to the vertices of G2. And so in this first example, you can easily see that these two graphs are actually isomorphic. They are the same. There's also this mapping from the vertices from the first graph to the second graph. And in this second example, you can also easily see that these two graphs are not the same. And the way to see this formally is that in the first graph, there is this vertex of degree 4, which cannot be mapped to any vertex in G2 in the neighborhood preserving way, because there is no vertex of degree 4 in G2. Now, the graph isomorphism problem itself has a wide variety of practical applications. One example would be symmetry breaking and SAT solving, where you want to remove the symmetries from a formula. And another example would be storing molecules in a database where you only want one copy for each isomorphic molecule. There are many more applications, which I could not list all here. But the point is that there is demand for fast practical algorithms for graph isomorphism. And now the interesting thing is that all of the state-of-the-art practical solvers that exist today are based on kind of the same paradigm, which is called the individualization-refinement paradigm. And so in this talk, I want to focus on these practical graph isomorphism algorithms, or more specifically, these individualization-refinement algorithms. For this talk, it's not really important to get into the weeds of individualization refinement algorithms, but I do want to mention some rough outlines of how the paradigm works. Assume you want to decide isomorphism for these two graphs, then the individualization refinement paradigm basically defines a tree, the so-called IR tree, for each of them. The gist is that in each node of the tree, a refinement is applied which partitions the vertices of the graph. Then the algorithm chooses a class of not yet distinguished vertices and artificially singles these out, or individualizes them, which defines the children of the node in the tree or the backtracking of the algorithm. So a different way is to view IR trees as the backtracking trees of IR algorithms, and it is both true that IR trees can be exponential in the size of the graphs, and IR algorithms are also generally exponential time algorithms. The different practical implementations do indeed apply different techniques on these trees, and so this might be a little bit of an oversimplification, but generally all IR tools are based around these same trees. In particular, all of them traverse these trees to solve graph isomorphism or some related problem. But since this talk is specifically about how to traverse these trees, we should now look at what specific traversal strategies are actually used by the practical solvers. There is a bunch of practical solvers which over the years have brought in many new and diverse ideas. I could not talk about what new ideas each individual solver brought in. However, since we want to focus on traversal strategy, the story is actually much simpler. The first individualization refinement solver, which was Naughty by Brendan McKay, was based on a depth-first traversal offset IR trees, and this is actually mostly true for all competitive solvers up until Traces by Adolfo Piperno, which was released in 2008. Now, the interesting aspect is that Traces is currently the fastest tool by using kind of a counterintuitive intermixed breadth-first traversal and random traversal of the tree. This of course raises the question, is that the reason why Traces is fast? Does traversal strategy actually matter? And can we come up with an even better, maybe even optimal traversal strategy? But even beyond Traces, there have been some attempts to improve traversal strategy. For example, there are strategies that try to exploit so-called isomorphism invariants, which I will talk more about later, even for depth-first search. Another example is a randomized IR algorithm called Screwbox, which exploits random paths of the IR trees, which I will also talk more about later. What all these attempts have in common is that the techniques are rather used as heuristics and not to improve the worst-case bounds of the involved strategy. But I should stress that we were absolutely inspired by all of the techniques. I mean, we use the same techniques. The difference is just that we apply them in a systematic way to get better worst-case guarantees. Beyond that, I should also mention that there is Rosenbaum's algorithm for group isomorphism, which uses collision probabilities to achieve a square root speedup for group isomorphism, which is also related to one of our strategies. Okay, so the goal is set. We want to analyze traversal strategies of IR algorithms. But in order to be able to do so, we need to get rid of some of the detail in order to make the analysis possible. In fact, we tried to strip away everything that is not related to the traversal. For example, even the input graphs we got rid of. What we got was a clean model of only the traversal in IR algorithms. And what is so nice about this model is that I can now give you the model in all of its detail without ever having to explain the IR paradigm properly. For the model, we first need to define special trees which model our IR trees. We call these trees black box search trees, and they have two important properties. The first is that no nodes have exactly one child, and the second is that all leaves are colored. I have three example trees here. Let's see if they fulfill the properties. The first one does indeed color all the leaves and has no node with exactly one child, so it is a black box search tree. The second one is a little bit more unbalanced, but still satisfies all the properties, so it is also a black box search tree. But well, the third one does have a node with exactly one child, so it is not a black box search tree. In our traversal model, algorithms cannot just access these trees however they like. There is only a certain way in which they get to explore the trees. For that, we first define that nodes of the trees can either be explored or unexplored. Algorithms only get access to nodes that are explored, and for explored nodes, they also get to know their degree and color in case they are leaves. In the beginning, only the root of a black box search tree is explored. Then the algorithms may explore more nodes by accessing an oracle in a very specific way. And so the way that works is that the algorithm gives an explored node to the oracle, and then the oracle picks uniformly at random a child of that node, which is then switched from unexplored to explored. So the algorithm can now access and make use of that child. The cost of our algorithms will then be measured in the number of oracle accesses, or the number of nodes which were explored in the tree. And so let's now just see an example of this in action. In the example, we start by definition with only the root node being explored. But we already know its degree, and if it was a leaf, we would already know its color, but it's an inner node. So the only thing we can do now is handing the root to the oracle, which picks uniformly at random a child of the root, in this case the right one, which is now explored. So let's now keep exploring on this right side, and indeed the oracle now reveals an orange leaf. So let's now explore the left part of the tree, which first reveals an inner node, then a blue leaf, then an orange leaf. And so in fact, we are now done exploring this tree. You might be wondering why we are done, because obviously there's still this one part of the tree that we have not explored yet. But however, we are still lacking one more very important property of the model. This property or axiom is called complete isomorphism invariance. What it says is that if there are two equally colored leaves, for example two orange leaves, then there must also be a color-preserving isomorphism of the tree mapping these leaves onto each other. Let's just look at our example again. Because there are two orange leaves, we know that there must be a color-preserving isomorphism mapping the orange leaves onto each other. But because it is an isomorphism, it must map the blue node to the subtree that is the sibling of the other orange node. And because it is a color-preserving isomorphism, that subtree must very specifically be a blue leaf. What you can see from this example is that sometimes it suffices not to look at the entire tree to actually know how the entire tree looks like. So maybe we can explore these trees in sublinear time. But for that, I first kind of need to tell you what we are even looking for in the tree. But what we are looking for is actually quite simple. Given two trees, we are looking for two equally colored leaves in both trees. And because of the isomorphism invariance axiom, this is the same as asking whether the two given trees are isomorphic. This is why we called the problem the isomorphism exploration problem. So the question becomes, can we solve isomorphism exploration in sublinear time? But before we answer that, we should maybe have a look back at IR algorithms to see whether the model is actually any good and whether the question is actually a good question. Since I skipped the part where I explained the IR paradigm in all of its detail, I will just try to give the main points of how the model actually captures IR algorithms. So, first of all, I should stress that actual IR trees do indeed also always fulfill the complete isomorphism invariance axiom, so this is a natural restriction that just applies. Also, the way we define the exploration in black box search trees is also just a way to define how general backtracking algorithms operate. And so the claim is that isomorphism exploration models the backtracking behavior of practical solvers when deciding graph isomorphism. One of the main arguments for that is that if we actually find a sublinear time isomorphism exploration strategy, we can immediately transform this strategy into an IR algorithm that experiences exponential speedup. The IR algorithm basically can get away with looking at less of its backtracking tree. In some sense, this means that the model is not too strict. Since we stripped away the graphs from the model, we don't actually consider whether trees that we look at can come up in practice. To fill in that gap, we have some follow-up work which characterizes what tree structures can even appear as IR trees stemming from graphs under certain assumptions. There we realize that actually for IR, the model is a little bit not strict enough. We would actually have to add some further restrictions for trees because not all trees can actually stem from graphs. However, this does not impact any lower bounds we give because basically we can give graphs that produce trees that are close enough to the ones that we use in the lower bounds. Okay, let's now get to work on some bounds for isomorphism exploration, but for that I should first tell you how we actually measure running time. We measure it in the size of the input black box search trees, either the minimum of the size of the two trees, which is denoted with a small n, or the maximum, which is denoted with a capital N. We look at three different kinds of bounds. First, an unrestricted lower bound, then a lower bound for bounded degree trees, and an upper bound. We look at three different settings. There is Monte Carlo, which allows randomized algorithms with error, then Las Vegas, which allows randomized algorithms with no error, but still with expected worst case running time. And lastly, a deterministic setting with no randomization whatsoever. We start off with the upper bounds where we simply provide algorithms which achieve that bound. Let's start with the easiest of the bunch, which is the deterministic upper bound of O of small n, which is the minimum of the two tree sizes. In order to run in the minimum of the two tree sizes, we need to interlock traversal of the two trees. We can do that by performing, for example, breadth first search in both trees in parallel, alternating between the trees after each explored node. If at any point we can distinguish the trees early, we just stop exploring. This achieves the O of n running time. But we should reiterate that sublinear time is good and linear time is actually bad. So this upper bound is actually bad, but later we will give a matching lower bound which shows that this is optimal. So we can simply not do very well in the deterministic setting. In contrast to that, we can give a very good upper bound for the Monte Carlo setting. Let us first make an observation. Assume we have two trees that are isomorphic. If you look at each level individually in these trees, the only difference between the trees is the different order of nodes or children of nodes. Now, let's say if we are performing random root to leaf walks, we start at the root and in each step we pick uniformly at random a child, then we can easily see that these random root to leaf walks do not care about the order of nodes or children of nodes. We pick them randomly anyway. If we want to find, say, a green leaf, we are equally likely to find it in the left tree or the right tree when we use random root to leaf walks. Remember that in a tree which is non-isomorphic to these two trees, we could never find a green leaf because of the isomorphism invariance axiom. And we can actually exploit this observation to create an algorithm. Now, this algorithm simply repeatedly probes these random root to leaf walks in both trees and collects the observed leaf colors in some sets. Then we create a probabilistic abort criterion based on the observation. Intuitively, we just wait for repetitions of these observed leaf colors. If we ever find a repetition of a color which was previously seen in the other tree, we found an isomorphism and we are done. But if we only ever find repetitions of colors within the same trees, it becomes more and more unlikely that the trees are actually isomorphic, because in the observation we saw that we would be equally as likely to find a repetition in the other tree if it was isomorphic. And so, since we are only looking for repetitions and we collect all the colors we see, we actually exploit collision probabilities here, which on some level is similar to the birthday paradox. Roughly speaking, the strategy will succeed after about a square root number of leaves are collected. The actual algorithm we use is a little bit more involved. We needed to add a doubling strategy for the length of the probe path in order to achieve the proper running time. This is needed because the trees can have linear height. They can be like really non-uniform. The details can of course be found in the paper. So this concludes the Monte Carlo upper bound. The only one that is left now is the Las Vegas upper bound, which is a little bit more tricky. While we can still exploit randomization and expected running time, we are not allowed to make any errors in this case. And so, similar to the bound for the Monte Carlo setting, the Las Vegas algorithm mostly runs in the square root of the size of the trees. However, in this case, we need to add the factor for the maximum degree of the two trees, which is d. Later we show lower bounds which prove that this additional factor is actually necessary. I will now quickly sketch out the idea of the algorithm. The algorithm is based on the notion of a split, which consists of a node v at a certain level h of one of the trees. We can solve isomorphism exploration based on such a split. The idea is that in the first tree, we explore one node v at level h and everything the entire subtree that is below v. In the other tree, we explore the entire subtree up until h, and then for each node at level h, we go down to one leaf node. Let's say that the trees are isomorphic. Well, then the isomorphic counterpart of v in the other tree must have been explored because we explored all the nodes at level h in that tree. For this isomorphic counterpart, we explored one leaf node below it. However, since we explored all the leaf nodes below v, its isomorphic counterpart must again also have been explored. So whenever the trees are isomorphic, the strategy ensures that at least one pair of equally colored leaves is found. However, while this strategy is certainly correct, the running time is kind of unclear. It depends on how large these explored subtrees are. To rectify this, let's for now call a split balanced if the involved subtrees are roughly d times square root of n sized. It should be at least easy to see that if we have such a balanced split, we can now fulfill the bound, even deterministically. However, the difficult question remains whether these balanced splits always exist, and if so, how we might find them. Let's assume we have a subtree of size 4 times square root of n. And let's now try to attach large subtrees, say of size 2 times square root of n, to this tree. Well, even if only a quarter of the nodes have such a large subtree attached to them, we have reached n, the size of the tree. So there cannot be more large subtrees attached. So if we were to pick a uniform random node at this level, chances are the subtree is small, and we have found a balanced split. Now, in these arguments, I did leave out quite a few corner cases, and I'm glossing over many details. The precise strategy we use is actually more involved, but I would say intuitively, this is the reason why this works out. The algorithm works down far enough in the tree, and then chances for a balanced split or something close become high. So this concludes our discussion on upper bounds. Let's talk about lower bounds. We again start with the easy ones, which in this case are the unrestricted lower bounds for Las Vegas and the deterministic setting. Consider non-isomorphic asymmetric trees of height 1. So these trees consist only of a root node and n leaves directly attached to them, where every leaf has a distinct color. For these trees, it is kind of easy to see that you simply need n+1 leaves to ensure deterministically that the trees are indeed distinct. And indeed, we also know that random regular graphs in practice almost surely produce such trees in practical solvers. The lower bound for the Monte Carlo setting is more involved. We prove an omega of square root of n lower bound for the Monte Carlo setting using binary trees, which immediately also imply lower bounds for the Las Vegas case, as well as the unrestricted lower bound for Monte Carlo, because it is the more general case. We show the bound using complete binary trees, where each leaf has again a distinct color. Again, I should remark that we know graphs that do produce similar trees in practice. The very rough intuition behind the lower bound is that the algorithms in the model are not free. We can characterize what they are able to do by saying they choose the structure how they will probe in the trees, but not which precise parts of the trees they get to look at. In a sense, they choose two structures T1 and T2, and the oracle chooses uniformly at random a root-preserving homomorphism into the actual trees. What we then prove is that if these structures, or how much they probe in the trees, are too small, then the probability of them getting mapped by the oracle to equally colored leaves become too small to decide isomorphism exploration. And so this is roughly how we arrive at these lower bounds. The last bound we show is the deterministic lower bound of omega of n in the bounded degree case. I think we kind of found a cool trick here by using the probabilistic lower bound to show the deterministic bound. Consider the trees from the lower bound again, this time with n squared nodes. Since the probabilistic lower bound also holds for the deterministic setting, assume there is a deterministic algorithm that considers sigma of n nodes. We then just run the algorithm and look at which parts of the trees the algorithm checks. Then we remove all the nodes the algorithm does not touch, which results in reduced trees of size O of n. But since the algorithm is deterministic, it still considers sigma of n nodes on the reduced trees of size O of n, which proves the bound. For me, it's also really interesting that the probabilistic lower bound uses very uniform trees and the deterministic lower bound very non-uniform ones. These non-uniform trees also seem to be intuitively the ones where it is harder to find a good split for. And this concludes our table. Overall, we can say that traversal strategy does indeed matter. Using randomization, we were able to provide near-optimal sublinear strategies. These strategies have in particular better worst-case guarantees than the strategies used in practice. We were also able to explain why some of the heuristics of traces seem very fast in practice, the discussion of which can be found in the paper. However, as promised, strategies in the model can also be implemented, and we did indeed implement the Monte Carlo strategy into a new solver which is called Déjà Vu. And as promised, it does indeed outperform other solvers for graph isomorphism, also in practice. The interesting thing about the Monte Carlo strategy is that it seems to have even more benefits in practice, which are not even captured by the model. For future work, there's still a logarithmic gap between upper and lower bounds, and we have not yet tried implementing the Las Vegas strategy. But that's it. Feel free to send me questions, and thank you for listening.